in order to keep the material so that it's able to extrude it easily.
Next, conveyors transfer the extruded compound to other machines that granulate and cool it. Then the powdery mixture passes through heated rollers that press it into a thin sheet. At this point, this humble material wouldn't stick to your fridge or anything else metallic. But now it's finally ready to pass over the simple device that'll turn it into a magnet. It's a roller consisting of powerful permanent magnets classified as rare earths. These particular rare earth magnets are neodymium iron boron and are positioned such that their north and south poles alternate along the length of the roller.
Before the sheet passes over this roller, the small ferrite particles in there are really not aligned magnetically in any form or fashion. As they pass over this, the field that is produced off of this rare earth magnetic roller aligns those little particles in the sheet to create a magnetic pattern on the sheet. And those would be a mirror image of what this magnetic pattern is on this roller.
Seconds after the sheet's bottom side is magnetized, a machine laminates its non-metallic top side. This is the side that'll stare back at you from your refrigerator, emblazoned with everything from calendars to the phone number of your local pizzeria. But before FlexMag ships the rolls to its clients who apply those touches, how can it be sure of its product's stick-to-itiveness?
One of the ways we make sure that the magnetic material is actually magnetized is we use sheet vellum. The vellum is actually two thin pieces of plastic with a liquid medium in between that holds fine magnetic particles that align with the magnetic pattern. And this material will show you the magnetic imprint on the magnetic sheet. As you can see, it's the same magnetic imprint that we used on the rare earth magnet roller.
Magnets have been leaving their distinctive mark on civilization for more than 2,000 years. And it all started with the discovery of a curiously attractive rock. Earth's magnetic poles have changed places hundreds of times over the past 400 million years, reversing the direction of its magnetic field. The last reversal occurred about 780,000 years ago. Magnets will return on Modern Marvels. We now return to magnets on Modern Marvels. For centuries, scientists have attempted to solve one of the animal kingdom's most perplexing mysteries. How do some species regularly navigate vast distances across the globe without getting lost? Recent studies suggest an intriguing solution to the puzzle. Researchers believe some animals use tiny natural magnets in their bodies that enable them to sense the Earth's magnetic field.
There is some evidence that birds and animals and fish use the magnetic field lines of the Earth to help them in their migration. They can find their direction, much like we do with a compass.
Just as animals may use magnets to survive in nature, we use them to sustain ourselves in a world of mechanization. Our enduring relationship with magnetism dates back to antiquity. About 2,000 years ago, the ancient Greeks and the ancient Chinese independently discovered Earth's only magnet crafted by nature. It became known as the lodestone, or magnetite.
It's an oxide of iron, and the basic properties of the lodestone come from its atomic structure, but how it's magnetized is still a bit of a mystery. We think it was lightning strikes hitting the rock and the magnetic fields from the lightning magnetizing the rocks.
Chinese innovators used the unusual mineral as part of a device made of polished brass. On its surface, a spoon-shaped lodestone was free to rotate in response to the Earth's magnetic field. It marked man's earliest step toward the first practical application of magnets, the compass. A compass's magnetic needle determines direction by aligning itself with the Earth's magnetic north and south poles.
If I place this in a little cup and allow it to float on some water so it's free to rotate, the compass will turn around and align itself pointing at the South Pole. If I reverse the magnet, the compass senses that the pole has changed and points the other way. Reverse it again, it swings back around.
By the 13th century AD, the compass changed the face of sea travel, relieving sailors from plotting their courses solely by the sun and stars. When storms obscured the skies, they could still ably navigate. In the centuries to come, the curious began to slowly unravel magnetism's mysteries. William Gilbert, physician to England's Queen Elizabeth I, led the way in 1600 with his landmark treatise, De Magnete. It was Gilbert who first concluded that the Earth was indeed a giant magnet. More than 2 centuries passed before an accidental discovery produced the next crucial breakthrough. In 1820, Danish physicist Hans Christian Ørsted stumbled upon magnetism's inextricable relationship to electricity.
Hans Christian Ørsted was the first to demonstrate that electric current down a wire would produce a magnetic field. He just had a compass needle near a wire. When the current went on, the compass needle turned. When the current went off, the compass needle turned back.
And he thought this was very curious. This discovery tied together 2 separate disciplines, electricity and magnetism. Ørsted discovered that they're really one and the same thing.
A decade after Ørsted discovered that electricity creates magnetism, English scientist Michael Faraday demonstrated the reverse, that magnetism can produce electricity. He found that moving a magnet near a stationary coil of wire, or moving a coil of wire within a magnetic field, induced electric current.
The oscilloscope is connected to the coil, and it reads the voltage that is induced in the coil. So you can see as I move the coil through the magnet, the spot moves up and down in response. The faster you go, the greater the voltage. So if you need more electricity, you have to move it faster.
Faraday's discovery was monumental. It paved the way for the invention of the electric generator, which enabled man to create electricity on a scale never before imaginable. The key to generating the power was to harness some form of mechanical energy in order to put the magnets or electric coils into motion.
In a hydroelectric plant, it's water falling over the dam through the sluiceway and turning the water wheel. In a coal-burning power plant, the coal makes steam and the steam turbine turns the generator. A wind power generator, the wind turns the blades of the generator. So the process is the same. Mechanical energy converted to electricity.
In the early 20th century, magnets were also empowering the reverse of this process, driving electrical motors that converted electricity to mechanical energy. The motors had eclipsed steam engines as the era's prime movers, propelling everything from trolleys to cranes to elevators. In a common electric motor, an electromagnet called the armature revolves between the north and south poles of a stationary magnet called the stator. The armature rotates